Hello, everyone. Thank you for coming to my presentation today. This is hybrid event shaping to stabilize periodic hybrid orbits. First, consider the example of the paddle juggler, which is a ball bouncing vertically on a paddle where impact is governed by a partially elastic impact law. For a hybrid system, we define a guard function G that triggers a reset map R that instantaneously switches the system's state. If we want to bounce this ball at a certain height and period, then the ball trajectory is fully defined by the position and velocity of the paddle at impact. In particular, open loop paddle acceleration has no effect on this trajectory. However, if we looked at the perturbed points of the ball near this trajectory, something interesting happens. We can see quite clearly that even though the acceleration term does not affect the nominal trajectory, it does have significant effect on the system's stability. We would like to know for general hybrid systems like legged robots, are there terms like the paddle acceleration that we can tune for stability? The key to unlocking this is the saltation matrix, which maps perturbations across a hybrid event from time t minus directly before impact to time t plus directly after. The saltation matrix is a function of the dynamics in each mode, as well as derivatives of the guard and reset functions. In general, the saltation matrix is a function of hybrid event time, state, and certain higher order shape parameters h. These shape parameters may appear in the derivatives of the guard and reset map that make up the saltation matrix reproduced here. The key with these shape parameters is that since they do not appear in the actual nominal dynamics of the system, they do not affect a nominal orbit and can be tuned completely independently for stability. This tuning for stability gives us hybrid event shaping. Hybrid event shaping is able to generate stable periodic solutions to many hybrid systems. Here is a point mass body with a massless leg that consists of a spring, damper, and actuator in parallel. A periodic hybrid hopping gate can be generated by solving for the necessary leg touchdown angle. However, this generated gate is highly unstable. So we set up a hybrid event controller for this leg angle that consists of a feed forward term, a feedback term on the forward velocity, and leg velocity at impact. The K and theta dot terms appear as shape parameters in the saltation matrix, and by choosing those values that optimize stability, we can generate a stable hopping gate. The final example I will present here is a kneed biped walker. Here, we use trajectory optimization to produce a trajectory while also shaping the timing and state parameters of the saltation matrix to optimize stability. We compared a hybrid event shaped trajectory optimization with a standard minimum energy cost function, which essentially plans the most efficient gate possible. In addition, we introduced the idea of virtual hybrid events, which are discrete control changes that are state triggered. These virtual hybrid events introduce additional saltation matrices to be shaped in the optimization. The bold lines here show the mean error results for 50 trials initialized with some initial perturbation, and the shaded region is plus and minus 1 standard deviation. The red plot shows the results of the minimum energy cost function, which diverges rapidly. On the other hand, both hybrid event shaped trajectories converge to the nominal trajectory, with the black including virtual hybrid events and the cyan not including them. In this work, we present the idea of hybrid event shaping, which finds optimal stabilizing parameters of a periodic hybrid trajectory. The saltation matrix is key to this because it gives closed form expressions for the shape parameters. The key contribution of this work is generalizing several previous hybrid controllers while also stabilizing more complex systems. Thank you.